All right, hi everyone. My name is Mark Kurtz. I'm the machine learning lead here at Neural Magic, where we work on improving inference speed for deep learning models, as well as reducing your cost for running those. And today I'm going to be going through pruning for success. So what do I mean by this? I mean coming in and being able to edit your model so that you can deploy it cheaper in production, as well as to deploy it more performantly. So one thing that I want to start off with is that most weights in a neural network are actually useless. And what do I mean by this? Well, most of the weights in a neural network can be removed with limited to no effect on the loss. So this is pruning. So let's say that we have an example fully connected network, like we do on the right. We're going to come in and actually prune some of those weights away. So some of those arrows, some of those connections, we're going to remove those, and we're going to remove those by setting those to 0. What we end up with is a not so fully connected network. And this actually works out pretty well. So to give some examples, ResNet 50, we can actually get that to 90% sparse. So we can remove 90% of the weights in the network and still match the baseline accuracy on the ImageNet dataset. MobileNet, we can get it to 75% sparse and still match the baseline accuracy on ImageNet. To go into NLP, transformers, we can get those to 60% sparse and still reach 99% of the baseline BLUE score on the WMT dataset, a language conversion dataset. So why is that useful? Well, the first thing is that we can do this to get faster inference time. So about 4 years ago, I was deploying a ResNet 50 model on a 4-core CPU. We were trying to predict images that were coming in from a user, whether or not people would like those, right? And in the deployment at that time, what I was able to get to was a few hundred milliseconds per image. This meant that anytime that we had spiking load, which we had a lot of, we would severely back up our queues. And we weren't able to actually process through those and get back to the user in time. It sometimes could take hours to get through those, even with several instances spun up in parallel. Well, let's fast forward to today. Today, the CPUs have gotten better and the software implementations have gotten better. So we can get down to tens of milliseconds per image. It really depends on the implementation. Some really good ones, like we have at Neural Magic, we can get to about 20 milliseconds per image on a 4-core CPU. And for other implementations, you usually get around 50 milliseconds per image. Well, if we come in and actually prune that model, we can get to sub 10 milliseconds, right? So a 2x decrease over the dense speed. So this means that, whenever you're deploying, you no longer have these queues backing up, right? 10 milliseconds is almost a long running function call. So this becomes very, very cheap to do. Another thing that makes it useful is reduction in size. So let's take another example. VGG16 is around 500 megabytes for the weights whenever we're storing it on disk. Another example is about 5 years ago, I was actually trying to deploy a model on mobile phones that we're doing augmented reality and trying to detect the walkable space in front of a user so we can navigate them through stores and through malls and airports and stuff like that. The problem was 500 megabytes is huge, right? If you go over 100 megabytes, you now require Wi-Fi to download any app. So ultimately, we didn't get to deploy it because we had that restriction. But with pruning, we can actually reduce VGG16 all the way down to 11.3 megabytes stored on disk because we're introducing so many zeros, right? So we get a 49x compression rate on top of that model. So now it becomes possible to actually not only deploy this model, but deploy multiple models into apps on the edge. And one big thing to note is that a lot of deployments currently are not taking advantage of this fact. We did a survey here at Neural Magic asking if, and one of the questions was, have you done any optimizations on your model, specifically for production, right? 58% of the 271 that answered this question said they weren't doing any optimizations. 24% mentioned that they were doing quantization, 22% said they were doing structured pruning, and then 11% said they were doing unstructured pruning. So the majority of people are actually not doing any optimizations to their models in production. And just kind of a quick note, the survey is still live, so we plan a tree for each response, and you're automatically entered for a $25 Amazon gift card. So we'd love to hear from you. Here's the link for that, and we'll make that available after. And we'll be sharing the results with the rest of the community soon as we can package them up. So getting back to the deployment, why are people not actually optimizing? Well, one interesting thing is whenever we dive into this is that data science team size actually makes a big difference. If your team is less than or equal to 10, only 6.7% of those people that answered had pruned. If your team was greater than 10, though, 18.8% have pruned, right? A huge, huge increase over that. But even then, it's still a pretty low number. So let's dive into some specifics. Traditionally, systems have not supported unstructured pruning for speed up. It's a tricky problem, and a lot of architectures actually just can't do it for speed up for any amount of speed up, like GPUs and other and certain types of accelerators. So a lot of them went the structured pruning route. Structured pruning severely limits the max sparsity you can get to. So let's go over an example for structured pruning real fast. Here's the unstructured network that we talked over before, right, where we remove those individual weights. And here's a structured comparison. So overall, these will get to the same sparsity level, but you can notice that whenever we're looking at this, these we got rid of 2 nodes here instead of the individual weights. What this means is that we're pruning away groups of weights. And it's very likely that since we're making an assumption that we can prune away groups, that we're actually getting rid of some of the weights that were necessary for us to converge on the loss. So kind of expanding on that, one big thing for pruning is that it takes a lot of learned intuition and iterations to do this. I'll go through an example or what pruning looks like on the next slide. But just know that it takes a lot of learned intuition, a lot of iterations, and this matches with why the team size correlates with how many people have pruned and not pruned, right? If you have a bigger team, you have more resources to put on things like this for optimization. And additionally, there's lack of support and ease of use in ML frameworks. So again, going back to team size, if you have a big team, then you can have enough people to spread across your organization that you can have people trying to focus on using these tools and learning these tools instead of spending weeks sometimes to try and figure out how to do it. So let's go through an example of pruning a network. One thing to note is that it's an iterative process. What I mean by that, we start from a trained model. We're going to go over a number of training epochs. Remove the smallest weights iteratively. What this looks like, and this is a TensorFlow example, where each of these are step counts. We're going to start, and then we're going to iteratively start removing weights. So on the left, we have our sparsity that we're getting to, and eventually we're going to end up at 85%, right? But we're going to iteratively do this over a certain number of training steps, and therefore epochs. And to kind of dive into this, why does this work? Well, new research is pointing to stochastic gradient descent being self-regularizing. So this means that any unused weights in the architecture, since it's so over-parameterized, are actually pushed towards 0. So all we're doing is removing those unused pathways in the optimization space. And then we keep the necessary ones, right? So now we can say that the magnitude actually correlates with how much that weight matters to the network. And another note on pruning a network is that the proper sparsity can actually vary drastically per layer, right? So fully connected layers versus convolutional layers, including different sizes, there's going to be different properties and sizes that depend on what the max sparsity you can get to for those layers are. So it's, channel sizes, kernel size, stride, all kinds of things. Ultimately, it boils down to a lot of how many parameters do you have to act on a certain amount of data flowing through the layer. But even then, it's not a hard rule because it also depends on the overall architecture of the network, right? So if you have complicated architectures like you see nowadays with CNNs, where they're doing compression steps or expansion steps or squeeze excite, there's all kinds of complexities that can really change the overall sensitivity for each layer. So what this leads to is a lot of hyperparameters. You now have a sparsity to set per layer, as well as how long to prune for, how often to prune, and a number of other things. So there's too many hyperparameters, and this is why it's so hard to do. And this is also why it requires so many iterations and intuition to find a workable solution, right? You have to prune away the solutions that are not going to work early on, so you can limit the number of iterations you need to get to a working solution. Well, how can we simplify this? Well, one thing that we thought of was, well, let's try and build this intuition into an easy to use user interface. We can allow the user to edit it further, right? So we automatically come up with a profile for them, a sparsity profile and automatic settings that allow the user to edit further based on that. And then we can constrain the choices based on the deployment environment, right? So some of the layers in these networks, if we prune them, actually aren't going to give us any speed up because they could be memory bound, right? So we're taking too much time to actually access for large data inputs to the layer. We're taking too much time to actually access this data, and any speed up on the compute actually doesn't help us. So we don't necessarily need to prune those layers. So we can actually constrain our choices based on our deployment environment. And then finally, we can save everything to a YAML file for continuous integration, continuous development. This makes all of these things that can easily plug into different data science tools. It can plug into Git, so you have your experiments saved and you can easily iterate on those experiments. And this gets into our UI. So we're still actively in development on this. This is a little bit more of the advanced user interface where you can see the different layers in the network, the sparsity level set for it, and how much each layer actually will give you for speed up for the network, as well as how much it affects your loss and how much it affects performance. And then, so the easier to use one is just going to have automatic profiles that you can quickly choose from. And we're actively iterating on that, and we'll be releasing that soon. So now let's step into the tooling. And what do I mean by tooling? Well, I mean actually doing the sparsity ops inside of your training process. So whether you're using TensorFlow or PyTorch or any of the ML frameworks, everything is really hard to use right now. It's really cumbersome and requires a lot of code. In some cases, like with TensorFlow, you actually have to completely redefine your graph to be able to do this. So if you're using pre-created models, like from the TensorFlow APIs or the Slim package, becomes impossible unless you're going to download that file and edit the original source code. So we want to simplify these implementations with an easier to use interfaces. So just to give an example, so this is PyTorch. This is just a very, very simple PyTorch training example where we're going to create our model, our optimizer. We're going to create some training data and then set our batch size. And then we're just going to loop over the epoch and the batches. And we're going to feed them through the model and update our optimizer. Well, taking that, we can actually, with only a handful of lines using our Neural Magic ML package, make it so that you can easily prune a model. So these few lines, so all that we're doing is we're using that config file that we mentioned earlier from the UI. We're going to create something called a manager and then an optimizer. And the optimizer just overrides the optimizer step and can be used just as is with any other optimizer. And we're just going to loop through exactly as we did before, and we're just going to tell it when the epoch starts and when the epoch ends. So all of this just configures with the config file, so we can make it easy to do. And so you need a handful of lines to actually just plug this into any training workflow. So this is a very simple one, but you can imagine how these training workflows can get much more complicated, and the integration is exactly the same. Well, let's say that maybe you don't want to do pruning, or you prefer not to do pruning altogether. Right, so you want to get all the benefits without any of the work. One thing we can do is actually transfer learn, because transfer learning works for prune models like it does for unpruned. And for Neural Magic, we're constantly adding more and more prune models to our repository for this use case. So all you need to do is download that model, transfer learn onto your data set, and you're good to go, and you don't have to worry about any parameters at all. So let's walk through a demo real fast. So what I have here is just a simple minced network example. All that we're going to do is it's all fully connected. So we're just going to have a number of fully connected layers and some ReLUs and go through that. So we have 5 fully connected layers, and we're just going to define our minced data set. So I've already pre-trained this one. I'll show you the training graph on this one. So this was the pre-trained run that I did before. And you can see that we got to about 98.7, right around there for our top one accuracy on our validation data set. And so let's go ahead and run that. We're just going to load those pre-trained weights. So we load our model, load our data set. Now, so since we're actively working on the UI, we just have a simple UI and for Jupyter notebooks currently. Right, so what we're going to do is just kind of set some hyperparameters for this. Since I know a little bit about this network, what I'm going to do is actually set the beginning and the end layers to 90% sparsity. So we're going to remove 90% of the weights, mainly just because these have fewer parameters. And then for the other ones, we're actually going to set those to 95% sparsity. So we're going to get rid of 95% of the weights. All right. And then we'll just save that config file real fast. And then let's run some pruning ops. So I'm going to kick this off. So I'm running on a GPU to train this or to prune this. We're just going to kick this off. So let me walk through what we did, because this is a little bit more complicated for the training flow. We use TensorBoard to log to. Essentially, all that we did to add in is we copied in, or we imported our necessary classes, and then we're going to instantiate those classes down here. So we're going to create our manager and our optimizer, and then after that, we just tell it for how long to train for, right? How long does the manager tell it to train for? And then we tell it to when the epoch starts and when the epoch ends, right? And that's all it is. So this is training now, and we can kind of take a look at how this is logging in TensorBoard. Let me get rid of that one and do this. So you can see that we're actively training through here. And you'll see on the KS modifier, we're actually constantly tracking the sparsity for the weights. So to jump back real fast, for all this, for all of our code, we make sure that we can easily integrate with TensorBoard. We have other loggers available as well, but TensorBoard seems to be the easiest. So all of this integrates with TensorBoard natively with just a few lines of code, and then we can actively run through this. So currently, looks like we're at about 52% sparsity, and we'll see that our top one accuracy is constantly going up. It should constantly go up, actually. So we're actively going through this. We're using the Atom Optimizer, and should finish in about another minute. Let's see. Okay, so a minute and a half. So again, we're just kind of going through and iteratively pruning away. So what we're doing is every epoch, we're going to remove the lowest weights. What this is allowing for is the optimizer to actually reorder all the weights as we're actively training, so that as we prune away new weights, it changes the solution or changes our optimization space a little bit, and then the optimizer re-regularizes. So you can see that we're getting kind of to the end now. We're getting up to almost 95% up here, and 90% for this one. I'm gonna go ahead and refresh. Okay, so almost there. One other note is just that you'll see the profile that it's not linear. The reason why is because early on, you can cut away a lot of the weights without affecting the loss at all. And later on, you want to make smaller steps, right? You want the optimizer to have more of a chance to regularize your weights as you're going through. So we finished pruning now, and let's take a look at our accuracy. All right, so we started at 98.68, right? And we're kind of hovering around 98.7, 90, depending on the run. So what this means is we were actually able to prune that network that I showed you up to 90 to 95% sparse and still get the exact same solution. And what this tells you actually is the fact that we're climbing a little bit still, so we could have pruned further. We actually could have made this even sparser. All right, let's see if we reached the end. All right, there we go. And then these last few steps, we're just going to export it to Onyx real fast. Onyx is a format that we use for our neural magic inference engine. And so we exported that to a local file. And all that I'm going to do is show you guys a comparison using our neural magic inference engine, we can actually run the unstructured sparsity for speedup, something that no other production system currently can do. So what we can do is use the MinstFC, our baseline. So we're going to benchmark that, and then we're going to benchmark the prune model that we just created. So let me go ahead and run that. Benchmarking dense, you can see our model coming out, and we came out to 6.73 milliseconds per batch. So we're running batch size 1024 from our previous data loader. So batch size 1024 right here. And our average dense came out to 6.73, and our sparse came out to 2.71. So we're almost 2.5 times faster for that sparse implementation, right? So these are things that you can take for compute savings, right? Be able to run through your queues faster and shut off the instances faster, or just get back to your user faster. So if you have a user waiting on a response on your website, this means you can get back to the user much, much faster. And then let me just kind of finish off real fast. Okay. So here are the citations from a few of the things that I put on there. And then finally, thank you guys for listening. Next steps, please talk to us about early access. We're actively trying to get customers in to evaluate the product. So please come by our booth and talk to us about that. And then finally, any questions from anyone? I don't know if I need to do anything.
Can you hear me, Mark?
Yep, I can hear you now. Okay, there we
I'm
go.
Sasha with Neural Magic also. I work with Mark. So there is a Q&A function in GoToWebinar. Feel free to ask any questions. We have a couple of minutes. One question that was asked is, Mark, can you comment on how you do pruning and effects on accuracy?
Yeah. So a lot of it comes down to how over-parameterized your network is. So overall, if you're pruning to low levels of sparsity, and whenever I say low, you can get to 50% is still kind of considered low. That actually helps out your accuracy because it's clearing out your optimization space. So it actually acts as a form of regularizer and actually can improve accuracy at these low levels. As we push the sparsity higher to try and get more performance, that's where we can start getting into a trade-off, right? So there I was around 94%, 93% sparse, and we're matching the same accuracy. So there's a little bit more there, but I'd be happy to talk with anyone if they have specific questions on trying to recover their accuracy. We have a few other questions coming in. So the first question is, does Neural Magic work in offline or secure environments? Yes, so we are actively working on that use case. Obviously, there are a lot of people out there that do not want their model shared anywhere, right? This is core secrets to their company. And yes, so we actively work in offline environments. We have licensing that we're working on to make sure we can run in those offline environments. So very, very good question. And then another question, will it run over TensorFlow distributed, or do you apply this after all model training is completed? So we do apply this after the model training is completed, but it still acts as kind of a final training step afterwards. So you can think of it as fine tuning after. And yes, we are running over TensorFlow distributed to make sure this works for it, because it does need to work with the entire training pipeline. Very good question as well.
Mark, another one that I just got in a different environment is, what are some features on the roadmap?
Yeah. So in terms of features, one big thing that we're looking at rolling out soon is Keras support, right? So being able to do this just as easily as you can in PyTorch and TensorFlow, doing the same thing for Keras as well for any users that are working in a Keras environment. Another big thing is actively iterating on that UI to constantly improve that so that it becomes as one touch as possible. So we can create these sparsity profiles for you automatically without you having to touch anything, right? And just be able to do a one-click button and it's good to go, so that you don't have to worry about all these different configurations. You can get from what you want, which is a performant model running in your infrastructure. So those are kind of two big things that we're targeting, and other things that we're targeting is monitoring for all of this. So as these models are running in our inference engine, making sure that you can actively monitor, right, which layers are taking the most time, so you can come back and actually do this pruning process or this recalibration process to change and kind of get a better life cycle on these architectures to improve your time in production.
Thank you, Mark. One more from a different also environment. It's not in the Q&A there. It goes, can I run a prune model on a GPU? What happens there?
Yeah, so GPUs actually, because of their structure, do not support unstructured sparsity well. There are a few things out there that do something called block sparsity, which is another form of structured sparsity where you're getting rid of large sections of your weights. So 32 by 32 sections of the weights. I believe this was released in PyTorch, and you can actually get speed up with those. The problem is that it's not flexible. The solution is not flexible. So you're getting rid of large chunks of weights, which means that you're getting rid of likely a lot of the weights that actually did matter for your solution. So you can't really get to anywhere near as sparse for these solutions. So the unstructured sparsity is something that we actually need a CPU for, because it's not as parallel and it has larger cache sizes to run the codelets required, the complicated codelets required for the sparsity.